Welcome to the Explainer. Today, we're putting on our detective hats and stepping right into the shoes of a code sleuth. We're going to equip you to hunt down and completely disarm the most common yet unseen programming logic traps in Python. Now, you know Python is universally loved for its clean, super readable syntax. But lurking just beneath that smooth surface are these invisible mechanics, quirks of memory, syntax, and flow that can introduce absolutely maddening bugs. So, we're dragging those mechanics into the light.
Today's agenda maps out our bug hunt. We're covering 1. Assignment versus equality, 2. Navigating control flow, 3. Lists and memory, and 4. Mastering slicing. Let's get right into it. Section 1. Assignment versus equality. To understand our first trap, which is the classic mix-up between assigning a value and asking a question, we actually have to rewind all the way back to 1957. As the legendary computer scientist Nicholas Wirth pointed out, Fortran's decision to use a single equal sign for assigning values just caused endless confusion. Think about it. For over a century, mathematicians used the equal sign to state that two things were inherently the exact same. But by making the equal sign an action, literally forcing a value onto a variable, early language designers created this semantic collision that we are still dealing with in Python today.
So here's how it plays out in Python. A single equal sign forcibly assigns a value. It's a command. It says, you now hold this data. On the flip side, the double equal sign is a question. It's asking, are these two things the same? It tests for equality and just returns a simple true or false answer. Confusing these two is honestly one of the most critical foundational mistakes a developer can make. It's pretty much a rite of passage for every programmer. But knowing this absolute distinction between a command and a question is your very first line of defense against code that inexplicably overwrites its own data when, it was just supposed to be running a check.
But hey, once you master that basic assignment rule, you can unlock some truly powerful techniques. Python allows for parallel assignment, which is awesome because it lets you unpack data from lists directly into multiple variables on a single line. Or think about variable swapping. In older languages, you'd need a clunky third variable just to swap two values. But in Python, you just write AB equals BA, and they magically swap concurrently. It's clean, it's elegant, and it completely bypasses the tedious assignment steps of the past. Moving right along to Section 2, Navigating Control Flow.
Let's see how this all builds into actually making decisions in your code. Control flow is exactly what it sounds like. It dictates the path of events. It uses branching statements to execute specific blocks of logic depending on the data it receives. The if statement opens the gate. If a condition is true, boom, the code runs. But what if you have multiple, mutually exclusive scenarios? Well, that's where elif, which is short for else if, and else come into play to catch all those alternatives.
The crucial point here is exactly how these branches interact, and this brings us to a major focus area, the if versus elif logic gap. A massive pitfall that so many beginners fall into is using a series of separate if statements when they really meant to use elif. Here's the deal. An elif branch only triggers if its specific condition is true and all prior conditions in that chain were false. If you just use a bunch of standard if statements, your program is going to evaluate every single one of them independently. That can easily trigger multiple blocks of code when you only wanted one to fire. Beyond just fixing logic gaps, using elif acts as a crucial structural safety net. Without it, checking multiple alternative conditions would require you to nest if statements inside else statements, which just pushes your code further and further to the right of your screen. This creates a deeply indented, completely unreadable mess that programmers jokingly call if-else hell. elif flattens all of this out, keeping your code readable and, most importantly, your logic absolutely airtight. Now, before we move on, let's just pause and think about this for a second. What actually happens under the hood if we assign two different variables to the exact same list? Like if I change one, what happens to the other? That brings us right to Section 3, Lists and Memory. This is a space where what you type isn't always what the computer actually stores. In Python, variables are really just name tags attached to objects in memory. When you assign an existing list to a new variable, say b equals a, you aren't actually creating a second list. No, you are just writing out a second name tag and sticking it onto the exact same list. This means mutations to one variable, like appending a new number to b, will silently affect a as well, simply because they are the exact same object. To manage that tricky memory behavior, we really have to look at the tools we use every single day. Take append versus extend, for example. Append drops a whole object right into the end of a list, even if it's another list. Extend, however, unpacks the elements and adds them individually. But here's the real kicker. If you want to avoid that shared memory trap we just talked about, you have to copy the list. But you got to be careful here. A standard shallow copy leaves nested inner lists vulnerable to that shared memory issue. If you have lists inside of lists, you absolutely must use a deep copy to create true memory-level independence.
And speaking of nested lists, I have to give you a serious warning about the list multiplication trap. Programmers often try to quickly generate a 2D grid by multiplying a list containing a 0 by 3, and then multiplying that whole thing by 2. It looks like it should create two completely independent rows, right? But it actually creates mirrored references to a single inner list. So if you update a value in row 1, row 2 automatically changes as well. It's a total phantom bug that drives people crazy. But spotting it right now is going to save you hours of future debugging time.
Finally, let's jump into Section 4, Mastering Slicing. Let's see how we can extract and modify data without falling into any of these traps. Slicing is basically like a scalpel for your data. It lets you cleanly grab elements using a bracketed syntax separated by colons: start, stop, and step. You define where to begin, where to halt, and the interval to jump by. And the beautiful thing is, you can even count backwards from the end of the list using negative indices. That means an index of -1 instantly grabs the very last item without you even needing to know how long the list actually is.
Let's actually trace this step by step so you can see it in action. Imagine a slice written as 1:7:2. First, we start at index 1. Then, we set our boundary to stop right before we hit index 7, and finally, we step by 2. This smoothly extracts just the targeted odd indices, 1, 3, and 5. It's incredibly concise and powerful once you get the hang of it.
But slicing isn't just for reading data, it's for writing it too. And here is a pretty wild feature. If you target a slice of a list and assign it a completely new set of values, Python will seamlessly delete the old slice and wedge the new data right in, even if the new data is a completely different size. It literally silently resizes your entire list on the fly. Seeing how a simple slice assignment can magically stretch or shrink your data leaves us with a final thought for our bug hunt today. If a simple slice can do all that, what other unseen mechanics are quietly running your code right now? Keep questioning the syntax, keep looking under the hood, and happy hunting.